So here we are with part 2 of chapter 2. We're going to knock out the second half of this chapter, and we're picking it up with now absolute value greater than problems. In the first video, we looked at absolute value equations and then absolute value inequalities with the less than symbol. So we have our first type of problem, absolute value of x minus a equal to b. Second type of problem we looked at was absolute value of x minus a less than b. And now we're going to look at the greater than situation. Okay, so I guess as if I was to write out some guidelines for solving these types of problems in any of these three cases, number one would be to isolate the absolute value bars. Okay, number two would be to let's say check for no solution. Okay, in any case where there's no option left for the absolute value to be positive, if the equation or inequality is forcing the absolute value to be negative, then there's going to be no solution. So check for those. Step 3 would be to separate the equation, the absolute value slash inequality into two separate equations or inequalities, whichever one you're dealing with. Okay. Step 4, solve each equation or inequality. In step 5, interpret the solution considering either the intersection or the union. Okay, and this step 5 really just applies to the inequality situation. If you solved an equation type problem, then you would just have your two solutions and you plot those two numbers or one number on the number line. In terms of an inequality, you either have to interpret it using an intersection or a union symbol. The intersection applied to the less than situation, and in this video we're going to look at the greater than or the union situation. Okay, and you can see in example 16 I've already got it worked out algebraically. What we've done is we've separated it into two inequalities, inequality 1 and inequality 2. And here you see a different symbol in between the two. We have a union symbol. Okay, and so on one hand we have inequality, and all we've done is drop the bars, and we wrote it the way it was given: x plus 5 greater than 3. We didn't change anything else, we just dropped the bars. The second inequality, we dropped the bars, flipped the inequality, and put a negative in front of the radius. Okay, now we've completed step 3, and now we perform step 4. which is to solve each inequality. So we subtract 5 from both sides, and we end up with part of our solution, x is greater than negative 2. We solve the other one, subtracting 5 from both sides, and we end up with x less than 8, or negative 8. Alright? And whenever you're solving these greater than problems, and you're interpreting it using the union conjunction, you basically just take your two inequalities and you dump them onto one number line. So, well, I drew the arrows wrong. This one over here, x greater than negative 2, actually goes over here to the right side of the number line. So, there's no equal to dash. At negative 2, we have an open dot and we shade to the right because we have x is greater than negative 2. And all of these numbers to the right are greater than negative 2. Now, the other inequality, it's going to end up over here on the left because we just have a negative 8. All right, so negative 8 is to the left of negative 2. And so we want numbers less than, not equal to. So we put an open dot. There's no equal to dash. We put an open dot at negative 8, and left is less. So we shade the number line to the left. Okay, and this is our final solution. If we were to write this in interval notation, we would start at negative infinity because we shaded all the way to the end of the number line to the arrow. So that represents negative infinity. Everything is shaded up until we get to negative 8. We close our parentheses because there is a gap. We put our union symbol in between the two notations, and then we pick it back up with negative 2. We put a parentheses because negative 2 itself is not included, and then we shade all the way to the end of the number line out to the right arrow, and that represents positive infinity. And with positive infinity, we end our notation with a parentheses. Alright, 17. There's some numbers surrounding the absolute value part of the inequality. So we need to isolate the absolute value bars before we get rid of the bars. Alright, so first step, add 14 to both sides. Fourteens cancel on the left. Now we divide both sides by 3. Threes cancel on the left, and we have a 7 on the right, and we still have the greater than symbol here. So we interpret our solution using the union of the two inequalities. Greater than union symbol. Alright, and specifically absolute value is greater than the radius. So we interpret the two inequalities that we get out of this one using the union of the two. Alright, now that we've isolated the absolute value bars, we will break it up into two inequalities. The first one, we just drop the bars and write it the way it was given. The second one, we flip the inequality and we make the 7 negative. We solve each one. This is an equal to dash, not a negative, so this is plus 7 minus 4, which gives us a 3. Now we divide by 3. and we get x is greater than or equal to 1. So this is half of our solution. To get the other half, we solve the other inequality. Subtract 4, bring down the less than equal to. A negative 7 and a negative 4 is a negative 11. We divide by 3. And we're dividing by a positive 3, so we do not flip the inequality in either of these cases. So 3's cancel, we bring down the x and the less than equal to symbol, and we end up with a fraction for one of our reference numbers for our solutions. Negative 11 over 3. And with this problem being a greater than type problem, we use the union, which is to say that we can just simply put both of the intervals on the same number line. So on one hand we have negative 11 over 3, on the other hand we have a positive 1, and we want numbers greater than positive 1, so we shade to the right, and then we want numbers less than negative 11 over 3, so we shade to the left. So here is our solution graphically. If we were to write it in interval notation, we would write negative infinity to negative 11 over 3, brackets, because they are solid dots, we have the equal to dashes. Then after the bracket we put our union symbol, another bracket for the 1, and then we end our interval notation with a positive infinity and a parentheses. So there's a lot of different ways that we can spell out the solution graphically. Interval notation, you could write it in set notation. You should at least know, definitely know the graphical and one of the other two, either set or interval notation. Okay, 18. Absolute value is already by itself, so we'll just go ahead and separate it into two inequalities, 1 and 2. And so the first one we just drop the bars, and then the second one we drop the bars, flip the inequality, and we could put a negative in front of the 0 if you wanted to, just to keep things, the procedure the same. But the negative is not going to change the 0, and so you could just put a 0 here. Now, we solve each one. X is greater than a negative 5 on one hand, and then the second half of our solution, x is less than a negative 5. And so notice in each one that we do not have the equal to bar. So x itself cannot be negative 5, but it can be bigger or smaller. What that's going to look like on the number line is we're going to have negative 5, and it's going to have an open dot, and then from there we shade to the left and the right. If you were to express this in interval notation, you would start with negative infinity, go up to negative 5, put a parentheses with a union symbol, and then pick it back up after negative 5 all the way out to the right at positive infinity. Okay, so you pretty much just skip the negative 5. It's the only number that doesn't satisfy the original inequality. Example 19, really just a question. What's wrong with the way this problem's written? And what we'll do is we'll just take this inequality and solve it the way we have in the previous few examples. We start out with a greater than symbol, and the absolute value is already by itself, and so what we have two inequalities. One of them would be a x minus 4 greater than 2, and the other one would be a x minus 4 less than a negative 2. Okay, if we compare these two inequalities to this compound inequality, then we can break this compound up into two inequalities likewise, and one of them is an x minus 4 less than negative 2, and then the other one, we take the x minus 4 greater than 2, so if you break them up this way, you get the same inequalities. So I suppose the only thing that's wrong is that when you write a compound inequality, it's understood that the conjunction between the two inequalities is an and, the intersection of the two. But the original absolute value inequality calls for the union, okay, the conjunction or between the two inequalities. So it's a slight difference in detail, but in this case I would probably say you don't want to break this absolute value inequality up into a compound inequality simply because of this reason. This understood to be an intersection situation, okay, which is not the case. So that's the big difference between the two. Okay, I'm going to save example 20 for you. The equation and inequalities are pretty simple to solve, but it may be a little enlightening if you were to solve each one and just compare what you get graphically from the number lines. So I'm going to skip over to example 21, and we're going to talk about now the graphs of absolute value equations. Alright, so y equals absolute value of x. If you've never seen the graph of this type of function, then you could just simply start by producing a table of values for y and x. And so what we normally do when we run into a function that we're not familiar with is we graph it with a table. So you start out by just picking a few numbers, a lot of times positive and negative numbers, and you pick those numbers for x. And so what we want to do to calculate y is to take the absolute value of these numbers that we chose for x. So absolute value of negative 2 is positive 2. Absolute value of negative 1 is positive 1. So y equals 2 for x equal negative 2. Y equals 1 for x equals negative 1. And then y equals 0 if x is 0, 1 if x is 1, and y equals 2 for x equals 2. So we just basically produce a series of ordered pairs that we can plot for our function. If you plot those points, you end up with something that looks like this. Okay. There is no curve to an absolute value equation. When you plot it, just the basic case, y equals absolute value of x only, there's no numbers mixed in, you end up with something that starts at the origin and basically looks like a V. Now, both of these sides are supposed to be straight. Apparently, I just can't draw a straight line. Something like that. And it's symmetric. Okay? Symmetric. Not sure if I spelled that right. I think it has two M's. But in other words, if you were to fold this graph along the y-axis, then both of the sides would be identical. Okay, they would overlap. So what's the domain of an absolute value function? It spans the entire x-axis. You can put in any x that you want, and you can compute a y. So all real numbers for the domain, but whenever you solve for the y, you'll see that you only get 0 and positive outputs. Okay, and remember, for the range, you can do what's called the horizontal line test. Alright, so in other words, if we go to our graph and we just randomly draw horizontal lines, some on the bottom, some on the top, okay, maybe you draw one right along the x-axis at y equals 0, what you'll see is only the ones at y equals 0 and above actually hit the curve. Okay, it doesn't matter how many times they hit them as long as they hit them once. So the ones up on the top, they actually hit our graph, but the ones on the bottom never hit it. Okay, so in other words, the negative values of y are not included in the range. No matter what number you put in for x, you cannot get a negative value back for your y, your output. So our range starts at 0, the outputs start at 0, and they go to positive infinity. Now, if we shift the graph, if we start adding in numbers along with the x on the inside and the outside, what that does is it shifts this graph up, down, left, and right. And so there's a possibility for the range to change. Okay. Now, if we add in a number on the inside with the x, what that does is it shifts it left or right, depending on the sign. And in this case, you could look at this as a -2, and this number on the inside of the bars is sort of counterintuitive, meaning that negative numbers actually move it to the right, and positive numbers would move it to the left. The number on the outside moves it up or down. And you can see that it's adding or subtracting. So if the number on the outside was multiplying the absolute value bars, that would be a different situation. We're talking about adding or subtracting a number. So in that case, if the number is positive or being added, then it shifts it up. If it's being subtracted or negative, it moves it down. Okay, so in this case, to graph this function, we take y equal absolute value of x and shift it, the graph of this, the basic, the parent function, shift it, let's see, right, 2 units, 2 is inside the absolute value, shift it right 2 units, and shift it, let's see, not down, but up 3 units. Okay, so if I were to draw my parent function, absolute value, it would pretty much look like this. A V starting at the origin. But if this -2 and 3 is mixed in, I wouldn't start at the origin now. I would start at y equal 3 and x equal 2, which is located right there. I would shift it right 2 and up 3. And so this is where my graph should actually be placed. Okay, this is the graph of y equal absolute value of x minus 2 plus 3. Alright, and so no matter whether we shift it left or right, the domain is going to work out to be the same, all real numbers. But now the range, we no longer start at the origin, we've shifted it up. So now the range starts at positive 3 and goes to infinity. Okay, this one. Okay, this next one is a little bit trickier. We can still find the starting point of our absolute value curve, but now it's not going to be the same v that we've drawn in the previous examples. In this case, we have a plus 1, so we want to relocate our y equals absolute value x. We want to shift it left 1, okay, left 1, and then we want to shift it down from the negative 2 down 2. So instead of starting here at the origin, we're going to go left 1 and down 2. So this is going to be our actual starting point here, not the origin. So let me draw our parent function in green. This is normally where it starts, just our basic y equals absolute value of x. Okay, but our new one is going to start here. And if the 4 was not included in our function, then we could just simply graph this as y equals x plus 1 minus 2. Now, the 4, what it's going to do is make our v sharper. And you pretty much have to either do a table of values or graph it with your calculator in order to figure out how sharp it's going to make your v. The only thing I can tell you is it's going to look more like this. It's going to be sharper. It's still going to be symmetric about this v point, but I can't really say how much sharper it's going to be. So you can still figure out where it starts, but in order to figure out a more accurate points for y equals 4, absolute value x plus 1 minus 2, you need to either do a table or pull up calculator. Okay, so in this case, what you can do is go to your y editor screen, type 4, go to math, scroll to the right, arrow over to the right for number, and the absolute value is the first function that we run into, and absolute value inserts our vertical bars, and then we type x plus 1, arrow over to the right until we're outside the bars, and put our negative 2, enter. And what I'll do on the next line is I'll graph it without the 4, and we'll compare the two. X plus 1 and the minus 2 outside, and graph them. Just hit the graph key. So here is with the 4, it's sharper, and then the other curve is without the 4. Alright, so if you need to graph it accurately, what you can do instead of actually calculating, inserting a number for x and calculating a table of values, is you can now go to your calculator, since it's graphed, and you want to go to the table menu. Okay, and under the table, here are the values for y equal 4 absolute value. Okay, it's going to be our first column, our first y column. Okay, so this will allow you by hand to graph a more accurate absolute value curve. So the 4 kind of trips us up, and so you're going to need to use your calculator in these situations. But you should at least know how it affects the absolute value curve. Okay, how does that affect our range and domain? Well, the domain is unaffected, and the range, instead of starting at the origin at 0, now starts at -2. It goes to infinity. It goes up. Alright, so we're going to wrap up the chapter with some application problems. 22, we're talking about the fewest points and the most points scored in a game. S is the score of the football team, and they've sort of encrypted that information, I guess you could say, into an absolute value equation. So in order to figure out what the fewest and most points are, we need to solve this equation. Alright, we have a equal sign. So what we do is we drop the bars, write the way it's given, and then we drop the bars and we make the right hand side negative. And we solve two separate equations that stemmed from one absolute value equation. In each case, we get the s by itself by adding 22 to both sides. We get s equals 44, and then we get, for the other equation, by adding 22 to both sides, we get s equals 0. So from here you can probably guess what the lowest and the most points scored were. Fewest was 0, and the most was 44. So a lot of times this just amounts to pulling out the absolute value equation or inequality and solving it as we normally would. 23 is talking about tornadoes. Here's our absolute value inequality. And so it's using an inequality to communicate a range of tornado speeds. Alright, and we have the absolute value part isolated by itself and a less than symbol. And so we're dealing with the intersection. Okay. So we break it up into two inequalities. The first one we just drop the bars. The second one we drop the bars, flip the inequality, and make the 28.5 negative. For both of them, we add 289.5 to both sides. And we end up with, let's see, we add these two. Let me pull my calculator back up. 289.5 plus 28.5 is 318. So the wind speeds were less than 318 or equal to it. solve the second inequality. Now we subtract the 28.5, and what do we get? We get 261. Alright, so in other words, having the less than symbol, interpreting the two inequalities using the intersection conjunction, we have a band of wind speeds between 261 and 318, including the 261 and 318. They get solid dots because of the equal to dash. And so this is our range of speeds for an F5 tornado, between 261 miles an hour and 318. And our last application problem, we sort of have to solve it backwards. We're given the limits of our body mass index being 18.5 and 25. Okay, the ideal is somewhere in between. So a person with the body mass index less than 18.5 is underweight, and whereas a person with the body mass index greater than 25 is overweight. Alright, and if you look at the inequality they gave us one with a less than symbol, and so we want these values. What inequality, absolute value inequality, represents these values in between? Okay, so with the less than, we're still dealing with the intersection. There's no equal to dash, so we have the open dots. And so what we need to do is find our center, A, and our radius, B. And simply replace the A and B in this absolute value inequality that they gave us. Alright, well, our two limits, the far right and the far left, are 25 and 18. So what we do is we just simply add these two together and divide by 2 to get our center. Pull up the calculator. 25 plus 18.5, and then divide that by 2, 21.75. And then our radius is simply, I usually take the bigger of the two limits and subtract the center from it. So 25 minus 21.75, we get, let's see, 3.25. Alright, so with these two numbers, A and B, the center and the radius, all we do is take them, both of them, and dump them back into our inequality. We keep the BMI. We write subtract 21.75 and then less than our radius, and I ran out of room. Let me scoot it over. We write BMI minus 21.75 less than 3.25. And so this is what we were looking for. And that completes the last example of the chapter, and completes chapter 21, or I'm sorry, not 21, but chapter 2. You got any questions, feel free to come by my office. Thanks for watching.